In this video, you will learn how the superposition principle of waves can be used to measure the wavelength of light. Let's assume that there are two light sources and a screen. We place a screen at a location X. These light sources emit light in all directions, therefore, light from both sources can reach the location X. Light in the form of a wave can be sinusoidal. At the location X, the electric field from source 1 can be written as the left equation. The electric field from source 2 can be written as the right equation. And phi is the phase difference from these waves. At the location X, these two waves meet. The light at the location X is the superposition of these waves from sources 1 and 2. The electric field at this location is the sum of the electric fields from these waves. We say that there is an interference of light from two sources at this location. If the phase phi is an even integer times pi, the electric fields from these sources add up, and the total electric field oscillates with high amplitude. We call this interference the constructive interference. We should observe strong light intensity on the screen. If the phase phi is an odd integer times pi, there is a cancellation of these fields. The total field can be zero or has a small amplitude. We call this interference the destructive interference. Let's consider another case. We still have two light sources. These sources generate the same electric field. We place a screen away from these sources. The distances from the screen to any of these sources are the same. The screen receives lights from these sources. The top equation gives the electric field at the screen from the upper source. The bottom equation gives the electric field at the screen from the lower source. Since the distances from the screen to the sources are the same, S1 and S2 are the same, and the phase difference is zero. On the screen, there is constructive interference. Then, we move the screen lower. For this new location, S1 and S2 are not equal. However, if the phase difference from the difference in distance is still an even integer times pi, the interference on the screen is still constructive. In the other case, if the phase difference is an odd integer times pi, the interference on the screen becomes destructive. Instead of having one location, we can have a screen that is wide. Light from two sources can reach any parts of the screen. The interference takes place everywhere on the screen. We can calculate the phase difference at any locations on the screen. If phi is an even integer times pi, there is constructive interference there. If phi is an odd integer times pi, there is destructive interference there. Next, let's define some characteristic lengths. The first one is the distance between two sources. We use d as this distance. The second one is the distance from the sources to the screen. This distance is perpendicular to d. We call it L. For one special case, with d much smaller than L, the light rays from two sources that reach the screen at the same location become close to parallel. The phase difference between these two rays is calculated from this delta S here, and the phase difference follows this equation. By knowing the angle theta between the vector along L and the light ray, we can estimate this delta S, which is d sine theta. Replace this new S in the equation for phi. We finally get the equation giving the condition of the constructive interference. In our experiment, there are hundreds of sources. We use one hue light source, and allow this light to go through a grating with 600 lines per millimeter. Therefore, there are 600 new light sources per millimeter from the grating. The light from the grating spread out in all directions beyond the grating. The angle for the constructive interference from these lights still follows the equation given here. The equation is still valid because any path difference from any pair of light rays share the same phase difference of an even integer times pi. In this experiment, we use a grating with known d, and we observe the constructive inference for n equals 1, and n equals 2. Since the light source emits light at multiple wavelengths, and each wavelength has constructive interference at different angles, we should observe a light spectrum. The angles from n equals 1 will be smaller than the angles from n equals 2. For each value of n, light with a smaller wavelength has a smaller angle. When we know the angle theta, we will use this theta, d, and n to find lambda from the equation above.